Okay, let's get started. Hello, everyone, and thanks for joining this training session. It's about timing constraint and trying to get a deep dive on timing constraint. Obviously, this subject could be a subject that we go through for a day. I mean, the original training can take up to a day. It's a very sensitive subject and often underlooked. Probably we spend more time in designing or writing the source code, and probably much less in timing constraint or putting our timing constraint for the design. So what we're going to try to do today is to cover the basics of timing constraint in an FPGA and discuss how the tools interpret them. I mean, every design is different, but the principle that apply in terms of timing are the same for all the designs. So we're going to discover a methodology on how to constrain our design and what are the things to look for, and how the tool interpret all the timing constraint that we put in our design. So if you have any question during the session, please feel free to put them in the Q&A widget, and we'll try to answer these questions at the end of the presentation. So my name is Murad Zakama. So I'm the presenter today. I prepared also the content of this training. I'm currently a part of the Lattice Insights training team. So Lattice Insights is the official training platform for Lattice. You will find all these type of trainings in pre-recorded manner, or also we have a unstructured-led type of training. So I have over 20 years of experience in semiconductor, of which 15 years are with Lattice Semiconductor, with different responsibility as a field application engineer, and strategic account manager. My main field of expertise, where I focus more, where most of the work I do are related to Lattice hardware and software, the tools associated with Lattice, obviously, the architecture of the different FPGAs that we offer, some design techniques and timing and the constraints and timing closure, that what we see today in this presentation. In terms of academic background, I have a double E with a master's degree in microelectronics and an MBA from the University of Quebec in Canada. Let's get started. So the agenda today has 5 sections. So we're going to start with some timing basics. So start from the basics in terms of the transistor and the different timing associated with the transistor and why they are important. You may heard metastability for a transistor. So we're going to understand what metastability is. Then we will discuss in section number 2 the timing constraint and how the software interpret them. And the third section will be more about the different types of timing constraints that you have in terms of either timing constraints or timing exception, and why do you use timing exceptions. And then we have to talk about the constraint priority also, which is a very important factor, as you will have to know how the tool prioritize things if there is conflicts in the constraint. So we're going to discuss that. And finally, we will end up with some timing constraint methodology, a proposed methodology on how to make sure that you have a very good coverage of your design, and how do you resolve timing constraint issue or timing closure issue. We're going to propose a 3-step process. So let's start with the timing basics. So we're going to talk about the flip-flop timing, the metastability of a flip-flop, and the importance of timing constraint in your design, and their impact on the outcome of the implementation process with a synthesis or map and place and route. So I think, I mean, everybody know that the flip-flop is the most important element of a sequential logic or a synchronous logic. It is usually referred to as a register also. So it has a D input and Q output, and the Q output will get the D input on the clock edge, whether it's a rising edge or a falling edge, depends on the design and depends how your source code is written. So this flip-flop, in order to operate properly, when I say properly, meaning that reliably, we can 100% be sure that the output will behave as expected compared to the clock and to the input that is provided. Certain timing parameters need to be satisfied. So if we violate any of these timing parameters, then the flip-flop get to an unstable state, meaning that the output becomes non-predictable. It could go to 0 or 1 independently of the input, which is not something that we would like to have for a flip-flop for our design. And imagine in a real design, you have thousands or hundreds of thousands of these that you need to make sure that they operate and they are safe operating range. So let's go a little bit deeper and kind of understand the flip-flop metastability. So like I said, if there's any timing violation, there's a very high probability. So this is a probabilistic situation that the flip-flop will get out of control and it will get back to normal operation afterwards. But for the next clock edge, probably you will be having some unknown status or unpredictable status. So this situation could happen if you have a setup time violation or a hold time violation. So what we mean by setup time is the data changing during this minimum setup time requirement, like we have here in this situation, where in the setup time requirement, there is the A input that is not stable enough or it's not stable long enough to be captured by the clock and be available at the output. So in this type of situation, the output that will come from the clock after the clock to out or the TCO is unpredictable. There is a metastability situation. So it could be 0 or 1 independently of the input. And that's what we try to avoid. So we try to avoid having the flip-flop go to metastability issue and affect, obviously, the design reliability or the design operation that you have. So the question that you may have, so how can we avoid a metastability situation and have a reliable design that is in conformity with the HDL code and the simulation that we have done on the design? So usually we perform functional simulation. It's very probably rare that we get to the timing simulation. But if we have a good functional simulation and you have a good timing constraint, there is a very high chance that your hardware will behave as expected, and there is less chances of having any issue in the hardware. And that's what we try to go through in the next section. So we need to have a proper timing constraint in order to make sure that our design is reliable. So let's look at the timing constraint from the software perspective. We're going to see timing and FPGA design flow in terms of where they interact in the design flow of an FPGA. So the timing constraint basis, what is a constraint when you have timing constraint, and talk a little bit about the static timing analyzer or timing analysis, which is short of STA, is the short of the static timing analyzer that is part of the Radiant tool. So we're going to see what is that and how to read that timing analyzer, and how does this tool calculate the different timing that is required to guarantee that your design will operate reliably regardless of what you have. Obviously, you have to meet your timing, but regardless of the design you're going to have a reliable design. So the first thing I would say in terms of timing in FPGAs, there's two types of timing constraints. There is the pre-synthesis timing constraint and the post-synthesis timing constraint. So what's the difference between these two types of timing constraints? So The pre-synthesis timing constraints are defined as timing constraints that are entered before any synthesis that happen on your HDL code. So they use the logical domain or all the components that are available before synthesis. So at this point, the objects that are available to constrain are available in the HDL code. Obviously, before any translation or before any interpretation from the synthesis tool. So the nice thing about pre-synthesis constraint is they could be transferred between different technology, between different vendors, and between different device family. And so they, on the other hand, the post-synthesis timing constraint are applied after synthesis and are used by the map and the place and route. And we're going to see diagram in the later slide and where they are input in each stage of the implementation. And they apply to the physical domain. So sometimes we are required to use post-route synthesis because some timing constraints that we need to apply are not visible in the pre-synthesis, and they are only visible after the synthesis. And that's where we need to use post-synthesis timing constraint. So in the post-synthesis timing constraint, you have access to the internal object. So these are instances, nets, ports, and after the translation of your design after synthesis. So an important note, I think I alluded to this in the previous slide. So the main reason for using pre-synthesis constraint is portability. So the timing constraint are only relates to the source code, and they could be obviously transferred between different device family, different vendors. Use it without having to change them every time. So the post-synthesis constraint, if you change your design, the net names, the instance names, and all the objects or the instances that are generated by the synthesis may have a different name, and you need to watch for these naming changes so you don't have your timing constraint or post-synthesis timing constraint ignored because the name of some of the instances has changed. So in general, it is recommended to use pre-synthesis constraints in order to maximize portability, but there is, like I said, situation where you need to have a post-synthesis constraint for your design. So pre-synthesis versus post-synthesis constraint. So you have the diagram on the right where you have the HDL code. The HDL code will go through synthesis, map, place and route, and after that you generate the bit stream. So keep in mind that synthesis tool, map, place and route, they are all timing driven. Okay, so the sooner or the higher in the flow you fix problems, the less chance you're going to have to fix them at later on in the design process. So pre-synthesis constraints are entered at the synthesis level, so they are an input to the synthesis level. Usually it's an SDC file, and the post-synthesis timing constraint is a PDC file. So they are very important to guide the tool. You can think of the synthesis tool and place and route. These are algorithms that will have an objective, and the objective is meeting the timing. So they will guide the tool to prioritize things so they can implement the design to meet your target timing constraints. So I think it is very important to make sure that your timing constraints are not overstated or understated, and that you have a very good coverage of all the timing paths at the high level, so you don't end up with the post-synthesis design that include extra logic or some paths that are not optimized by the synthesis that you have to carry on and try to fix at the map level or at the place and route level. So it's important to fix these timing problem at the higher level so you don't carry them later on, and where it becomes probably impossible or very hard to fix later on. So I think I mentioned this. So the constraints or the lack of constraints at the higher level will have an impact on all the lower levels. So make sure that you work from the higher level down in terms of integrating your timing constraints. So what should we constrain for a design? So the tool or the timing constraint should constrain any flip-flop to any flip-flop connection. So any time you have a path between two flip-flops, you need to make sure that that path has been constrained and that the data is transferred reliably between the different flip-flops that you have in your design. So in this case, we have a device A, FPGA, and a device C. And the device A will be driving some signal to the FPGA, and the FPGA will be driving some other outputs to the device C. So the different paths that need to be analyzed and need to be constrained are all these paths. So the device A to FPGA, which is an external path, a timing path to the FPGA, but need to be constrained also. So the way timing constraint work is on a system based, not on specifically on the FPGA, because the FPGA is receiving these signals from an external device. So we need to make sure that the FPGA knows, or the timing analyzer, the STA tool knows the timing associated with the driving device, or with the device that is driving the signal, with the flip-flop that is driving these signals. So it's basically the TCO, the clock to out, that is associated with this device, or the flip-flop that is driving the signal to the FPGA. Then we have the internal paths, obviously. So any flip-flop to flip-flop connection within the FPGA need to be constrained. So if you have a simple clock domain, one clock domain, this is very simple, but you have multiple clock domains, you need to make sure that you constrain all the different clock domains. And obviously the output path, or the external timing path for any signal that is being driven from the FPGA to external device. So what is STA, static timing analysis? So STA is a method of analyzing the performance of all possible paths in a given design, and making sure that we can guarantee the operation of these devices across voltage, temperature, and process variation. Voltage, temperature, and process voltage and temperature variation, sorry. So the paths that are analyzed by the STA tool are all these paths. So input port to flip-flop, and internal flip-flop to flip-flop, and flip-flop to output ports. And for each one of these paths, like we've seen in the previous slide, you have two timing that are used. So there's the required time and arrival time. So the slack will be the difference between the required time and the arrival time. In case we have a positive slack, that means we meet the timing requirement with a certain margin. In case there is a negative slack, that we have a timing violation, then the design is not reliable, and we have to make sure to fix that and not try to go to hardware with that type of an issue. It may work in the hardware, but you may end up with an intermittent problem that you try to fix for a long time without easily finding the issue. So it's very important to make sure that we meet all the timing when we go through the design analysis or timing analysis. So the static timing analysis is performed at a different level. So this tool provides you different reports. So you can have a report after synthesis, or after map, and after place and route. So obviously, when you are at the synthesis level, the timing report does not include an accurate information about the routing delays. It's an estimate value of the routing delays, whereas in the place and route, after place and route, this is the most accurate timing report. The information that is available in all these three reports provided by the STA tool are the same, but the accuracy is different. The post place and route STA tool is the most accurate. We may sometimes look at these early timing reports just to make sure to identify any issue early enough before going through place and route that may take longer to go through. So just keep in mind that the most accurate timing report is the post place and route timing report. So what is the STA calculation process? So it's independent of the design. Any design will go through this process. So you will have these two timing analysis that is performed by the STA tool independently of the design. There's a setup time analysis and a hold time analysis. So like we've seen in the flip-flop, it's exactly the same thing. So we are making sure that there is no setup time violation for all the flip-flops, meaning that the data is stable enough before the clock edge to guarantee the transfer of that data to the next stage by the flip-flop. The hold time is the same way. So the hold time is the amount of time that that synchronous element, the flip-flop, has to have the data stable after the clock, so it does not corrupt the data output or go to metastability situation. So we're gonna talk and we use the timing path. So what is a timing path? So the timing path starts as a clocked element. So any path that starts as at a clocked element and ends at a clocked element is checked for these two timing analysis, so setup time and hold time analysis. So when we talk about clocked element, I mean, it's not only the flip-flop, it could be a blockram, because the blockram output will have some flip-flops to clock the data out. Also, it could be DSPs, any other primitive that has a flip-flop element in it will be analyzed. And that's the job of the STA tool, making sure that any synchronous logic that you have in your design is checked for the setup time and hold time analysis. So let's see how the STA tool works and how all these paths are analyzed. So we're gonna focus on the internal FPGA paths and how the setup time and hold time analysis is done on these internal paths. So if you look at the setup time analysis, it is always done on the next edge. So if we assume that the launching edge is the first edge that we see in the timing diagram of the clock here, then the setup edge will be the next edge. That's when the setup time check or the setup time analysis will be done by the tool, okay? So let's take some examples of calculation process. So this calculation process is the same. You can look at the STA report. You're going to see that it follows exactly the same process that we're going to go through in this slide. So how does the slack calculation work in the STA tool? So the first step, we're going to calculate the clock source delay, which is T1 that you see here. So the time it takes for the clock from the input port of the FPGA to get to the first flip-flop. So that's the T1. So it's going to include the input buffer, any routing delays till it gets to this flip-flop A. Then the step 2 will be calculating the data path delay. So how long it will take for the data to travel from flip-flop A to flip-flop B. So any logic or level of logic that are included between the two flip-flops will determine obviously the delay that is associated with this path. Then the third step is the calculation of the destination clock, the delay. Actually, there's a small difference between the time it takes for the clock to get to the flip-flop A and the time it will take to get to flip-flop B. And that difference will be calculated and will be used to calculate the slack of the setup time slack. So if we have the TP is the period, the clock period. Then arrival time is T1 plus T2, and required time is the TP, or the time period, plus the time it will take the clock to get to the destination flip-flop. And then the setup time check will be required time minus arrival time minus clock uncertainty. So let's assume clock uncertainty is 0 for now. The slack will be the difference between required time and arrival time. So we've tried to represent this in the timing diagram that you see on the bottom right. So we have the clock, we have the launching edge. So when we clock the data, it's going to take some time for the data to be available out of the first flip-flop and have a data valid data after a certain TCU time. And once the data is stable at the flip-flop A, then we will go through some logic delay plus routing delays. And after that, the data will be evaluated for setup time and hold time analysis. So that's where the setup time is done. Setup time analysis is done, and as you can see, there's a small difference between the clock. That's the T3 basically, and the addition of these two is T2, the T2, and the clock delay. T1 is the delay it takes the clock to get to flip-flop A. So this is exactly the same process that will be used for every single design, for every single flip-flop. Obviously, in the STA report tool, not all the paths will be reported. There is a setting in the tool that will allow you to determine how many paths are reported, but usually by default, you have the top 10 worst path will be listed with their details. So you can look at the timing violation and fix them if you need to. So this is a simple case where you have one clock domain, but let's say we have, yeah, so let's go, I mean, it's just an example of the same information. So let's go through the example, like just with numbers. So the time period is 10 nanosecond. We have T1 as 0.5 nanosecond. The time it will take for the clock to get to flip A is 0.5 nanosecond. The time it will take to propagate the data between the two flip-flops is 7.5. And let's say it will take a little bit longer to get to flip-flop B. Let's say it's a 1 nanosecond. So arrival time is T1 plus T2. So arrival time is 7.5 plus 0.5, which gives you an 8 nanosecond. And the required time is the time period, which is 10 nanosecond plus T3, which is an 11 nanosecond. So the required minus arrival is a positive slack. So that's a 3 nanosecond slack, meaning that you meet your timing and you have a extra time or a slack of 3 nanosecond for your design, which is good. So let's take a more complex example where we have two clock domains. So let's say we have a 200 megahertz clock domain and 133 megahertz clock domain. And you can see that this is the timing axis with the different nanosecond timing of the different edges that you will have in your design. So how are we going to go through the timing analysis for this case? So the steps are exactly the same. Keep in mind that if there is no indication of the relationship between clock A and clock B, the software will assume that they start at time 0. So they both start at time 0, and it will lay out all the waveforms like you see in here. So the difference here is that the launching edge and the setup check edge is different because we are moving from one clock domain to another clock domain. So, and there's different possibility. You could go from this clock edge that you see here. So let me take the pointer probably. So you could take the data from this clock edge and check it at this edge, but there's a possibility also that the data is clocked at this edge and it will be checked here. And there's a possibility that we clock it with this edge and we check it at this edge also. And you can see the difference between the timing for all these situations. So you have a 7.5 nanosecond here, you have a 2.5 nanosecond here, and you have a 5 nanosecond here. So which one we should use? So the STA tool will use the worst case scenario just to make sure that all these situations will work. And in this case, it's a 2.5 nanosecond timing constraint. And you may wonder, I mean, in the timing report, you may see that certain timing paths are constrained at 2.5 or 400 megahertz, but there is no clock that is running at that speed. And that's the case when you have this type of situation where you have a PLL probably generating all these two clocks from one main clock, and there is a relationship between the two. So the tool will look for the worst case scenario and constrain the whole design on this worst case scenario. In the case of this is what we call the clock domain crossing situation. And ideally, I would say we need to cover that by some CDC circuitry, either FIFO in between or some cascaded register to avoid the metastability situation. I mean, that's the best case, or that's the recommended way of dealing with clock domain crossing. So, and making sure that you don't have any timing violation. So in that case, you may want to tell the software that these paths are going from clock domain A and to clock domain B is a false path. And that's where the timing constraint exception will get involved, just to make sure that the tool understands that you covered that by design and no need to analyze the clock domain crossing, just analyze clock A and clock B, for instance, okay? So for the calculation process, in terms of different clock domain analysis, we have the arrival time exactly the same, so T1 plus T2. So the time it takes for the clock to get to flip-flop A plus the propagation delay of the data. And the required time, instead of being the period, it is the Tx, which is the shortest distance from clock edge, one clock edge to the receiving clock edge, plus T3, which is the time it takes to get to for the clock to get to flip-flop B. And then we do the same calculation, so required time minus arrival time minus clock uncertainty to get the slack of the setup time. So if we take this example that we've gone through, just going through the numbers just to make it look more real. So we have a 200 megahertz clock and a 133 megahertz clock. So the period of the clock is 5 nanosecond and 7.5 nanosecond for clock B. And let's assume that there is 0 nanosecond uncertainty for the clock. Then we have these timing T1, T2, T3, and Tx. Like I said, Tx is 2.5 because we have the worst case here. Then we have arrival time T1 plus T2, which is 5 nanosecond. And required time is the Tx, 2.5 nanosecond, plus the 1 nanosecond for T3, which is 3.5 nanosecond. So if we calculate the slack in this situation, we have required minus arrival, which is 3.5 minus 5 nanoseconds. So we have a slack of minus 1.5 nanosecond. This is not good, meaning that we have a timing violation. And this is where it comes to knowledge of the design and making sure that you understand what's going on. And if this situation is covered by design, you need to tell the STA tool to ignore these paths so it doesn't analyze and doesn't try to optimize it to hit the 400 megahertz clock or the 2.5 nanosecond requirement for that setup time analysis. Okay. So let's take a look at the timing constraint types. So there's multiple types of timing constraints, and I group them in two categories. There's the timing constraints that allow you to constrain your design, like create clock. The create clock will allow you to identify a clock and constraint to a certain value. This could be a real clock or a virtual clock. We actually have a full day of training on these. Please refer to Lattice Insights, and just to have more details on this, or to the documentation, I have a reference slide at the end to go through the different references that you can go to in order to get more in-depth details on these. There is also create generated clock. So generated clock is a clock that you generate in your design, unless you tell the software or the STA tool that that's a generated clock. The relationship between the original clock and the generated clock will not be known by the software, and hence the timing analysis will not be done the right way if you don't indicate that to the software. And I'm not talking the situation about a PLL. So PLL will automatically be identified by the tool, and the relationship between the input clock and the output clock will be automatically identified. But I'm talking more about, for instance, clocks that are generated by clock enable situation, where you may be enabling the clock 1/4 of the time, for instance. Clock latency, just defining the different latency of the different clock uncertainty could be defined also in the timing constraint, just to give more information about the clock. Clock groups, clock groups allow you to identify different groups of clocks, and if they belong to different groups, if clocks belong to different groups, then the STA tool will not analyze in between clocks timing. So making sure that, like in this situation we've seen for dual clock domain or dual clock situation, and clock domain crossing timing analysis, if we put clock A and clock B in different groups, then the STA tool will automatically ignore any timing paths between the two. But you have to be careful when you do that to not do it without knowing the consequences of this. Input delay. So for any constraint, any input path to the FPGA, we use input delay, and we reference that to a virtual clock where we create here. So, and output delay are all paths that are output from the FPGA to another device. So once, I mean, we do all this, we have our timing constraint covered, and we may look at exceptions. So these are the exceptions require the understanding of the design and making sure that we give more indication or more information to the STA tool and to the synthesis tool, place and route tool, about the relationship or the non-relationship of the different clocks that you have in your design. So set false path will indicate that a specific path should not be analyzed by the tool. Multi-cycle path, if you have a situation where you have a data enable, for instance, that is only enabled for 1/3 of the or once every 3 clock cycle, then you may indicate that to the tool. So the timing analysis will be relaxed for that specific path and focus on other more important, more critical paths. Max delay, min delay for any nets that you have in your design. Max skew, if you have a bus and you want to make sure that the skew between the different bits of the bus are minimal, you can define that in max skew. So there's much more details. I try to go through these different timing constraint with some level of details here, but please refer to the documentation to get full understanding of all these timing constraints. In the Lattice Insights, there is a complementary course that you can look at. So developing with Lattice FPGA and sending design constraints, where we go through the details of all these different timing, including the use of the constraint editor, the constraint propagation engine, and all the different recommendation in terms of timing constraints. So please feel free to sign to the Lattice Insight and have access to this information. So the timing constraint editor is a tool that we have available in the Radian and Diamond software platform that will help or enable you to write all these timing constraints. So you could write an SDC file by just writing an ASCII file, a text file, where you put your text, you put all your timing constraint directly on that text file, but you have to know the syntax. So the point of the pre-synthesis or post-synthesis timing constraint or constraint editor that is part of Radian needs to make that job much easier without necessarily knowing all the details of and the option associated with each one of the timing constraint. And there's multiple tabs that you can see here. So there's a clock tab, generated clock, clock latency, clock uncertainty, clock groups, input output delays, and timing exception. And these are exactly the same that we've seen in the previous slide in terms of timing constraint. And you just double click to have a window that will open available clocks that you have in your design, and then specify the period or the frequency, and that will automatically write the timing constraint for you. So it's a very handy tool that is part of Radian. And in order to reference object in your design, you have to provide certain indication about what object you are referencing. So this timing constraint could apply to ports, and what we reference, what we mean by ports, or what we reference when we mention ports, are the inputs and outputs of the FPGA. So these are all ports of the FPGA. And pins will be the inputs and outputs of instance names that you have in your design, or primitives that you have in your design. That's called pins. The nets are obviously the nets that you have inside the design that interconnect the different instances or components that you have in your design. Then you have the clock, cell, or blocks. Okay, so the clock is obvious, the cells or blocks are all the cells or blocks that are part of your design. And in order to reference these objects, you have to use the get ports, get pins, get cells, and get nets with the different options. And like I said, there's much more details in the documentation about these that you can reference to. So constraint priorities and resolution. So now that we've gone through the different types of timing constraints and how the STA tool works, it's important to understand in case of conflict, how does the tool resolve that conflict? So there's different rules that are in place to make sure that the tool does the right decision every time, but the user has to know these rules, right? So to make sure that timing constraints are not ignored because they are done in a wrong way. So different types of rules that we're going to go through. So entry type, constraint order, timing exceptions, and path details. So let's go through all of these. So first thing, constraint priority is based on entry. So it depends where you enter the timing constraint. Are they at the post synthesis constraint? Are they post synthesis, meaning PDC file, or they are pre-synthesis, or they are at the strategy option or the setting and the tool? So PDC will take precedence. So will take highest priority over all these different options. So let's say you have create clock, minus clock 5 nanosecond, meaning period 5 nanosecond, and you put this in the SDC file. And then in the PDC file, which is the post-synthesis constraint, you put a 10 nanosecond here. So this will be used only for synthesis. The SDC will be used only for synthesis, whereas the PDC will be used for the implementation. So that will be the one that will dominate on the implementation side or on the place and route side. You may want to do this because you're trying to have the synthesis tool do harder work and relax things for the place and route. But just you need to be aware that in case of conflict, the PDC file is the one that will take it over. So the order of how these constraints are entered into the design are important, even if they are part of the same SDC or PDC file. In the case where you have, for instance, create clock and you have 5 nanosecond, and you forgot that you defined this, when you have in the second line a 10 nanosecond, then the second line will take over the first line. unless you have this add option where you want to apply two constraints on the same object, then you have to use the -add in order to do that. So same thing applies for set input delay and set output delay, the same thing. So unless you use -add delay, then the second one would override the first one if they are referencing the same object, like in this one, in1 is referenced in the same way. So there is also a priority associated with the timing exceptions. The highest priority goes to the clock groups and false paths. So if you declare some clock groups, meaning that clock domains that are not related, or false paths, these will take precedence. The paths will not be analyzed. They will not be optimized for the related timing constraints that is associated with them, because they are false paths. The second priority is set max delay, min delay, and the third priority is set multi-cycle path, and that's the lowest priority. So just be aware of when you use timing exception that there is priority associated with them, and you may think that you have a timing constraint, but it gets ignored because it has a lower priority than the other two. The number of details that you have on a certain path matters. So the more details you have, the more specific the description of the timing constraint, the higher priority it will have. So in this case, the first priority will go to anything that has, for instance, from, through, to, and if you have less details, then it becomes lower priority. So let's say we have in this example set max delay from get clock 1 to get clock to get pin register 1D of 2 nanosecond, and we have set max delay from clock 1 to clock 2. So obviously the first one will take it over, because when you specify an instance or a pin in an instance, it's more specific than two clock domains that are listed here. And the first timing constraint will take priority precedence and will be used. Okay, so there's much more details. I mean, we cannot cover a lot, much more than what we covered in this session. So, but please refer to all the documentation available on this subject and the time enclosure session that is also conducted by my colleague Sukrot on this matter. So I'm going to propose a three-step process here to do time enclosure. If we follow these steps, we should be good in terms of having full coverage of our design. So the first thing you should do in step one is identify all the clocks that you have in your design. So for each one of these clocks, whether virtual clocks or real clocks, you have to associate that with the timing constraint. So you have to do create clock, the name of the clock, the period. So the tool knows that it has a target, and there's a target for each one of the clocks. Same thing for the virtual clocks. So when you have virtual clocks, meaning that you have external devices to the FPGA that are driving signals to the FPGA. So identify these and create the virtual clocks that are required. Then, based on how the HDL code is written, make sure that if there's any generated clock, identify them and mention them, or create a timing constraint to indicate that to the tool, create generated clock, and the relationship between the original clock and the generated clock, like in this case, divide by 5, for instance. And then once you've done that, you define your input and output timing constraints, and refers to the virtual clocks that you created in this step. And then you define any clock characteristic, whether clock uncertainty, clock latency, any different clock skews between the different clock domains, and so on. If you do all these 5 steps, you should be good to have 100% timing coverage of your design. I mean, there's no reason that you don't get that 100% coverage. And it is important to have a high coverage, like we said, to avoid any hardware failure or intermittent hardware problems that you may see in the lab, and that will take weeks probably to fix in some cases. So once you've done that, you could, if you want, after doing all these steps, I mean, if you meet your timing after doing step 1 to 5 and the design meets timing, you're good. I mean, I don't think you need to do more things, but you may be in some situation required to define some timing exception just to help the software meet the requirement for your design and understand better the different relationship that you have in your design in terms of timing. So that's the step 1. So setting up timing constraint, making sure that you have 100% coverage. Step 2 is timing result analysis. So once you set all your timing, you run the tool and you get some timing results. So you go through these steps to make sure that the timing constraints are accepted by the software. So in the timing report, there's sections called 1.1 SDC constraints. So these are the resolved timing constraint. Make sure that whatever you expect to see in terms of timing constraint is listed here, because that's the one that is adopted by the STA tool. If there's anything ignored or deleted because of priority, because of conflict, and so on, they will not be listed here. So make sure that whatever you see here is what you expect to see. Then the second thing, make sure that you have 100% coverage, or at least check the constraint coverage, and you're comfortable with that. I mean, my recommendation is to shoot for 100%. If you are higher than 90, you should be good, but I think the target should be 100%. And if these timing paths that are not constrained, then you can refer to a section 1.3, which will report all the unconstrained paths, and that will help you add the timing constraints that you need. Then you go to the setup time check, which is section 2 of the timing report. And if you meet all the timing, I mean, no further steps needed. You're good to go. You should be fine. If there's if not, I define some timing paths that fail the setup check or the hold check, then these will be listed in section 2.1 and 2.2. You can refer to the details of all these paths in section 2.3. I think the first thing I would look at is the percentage ratio between the logic and routing. This is a good indication. Are we talking about a logic issue or routing issue? Sometimes you have a component that are placed somewhere in the fabric because of physical placement. Let's say you lock a pin in certain region of the device, but you have another piece of logic that is physically located somewhere else in the floor planning of the device. Then there's a long routing delay, and that will give you a good indication where to look for fixing the problems. If you see 90% logic and probably 10% routing, you may be having an issue in terms of the number of logic level. You maybe you need to add some pipeline register, look at the source code, understand what's going on there. So I think this factor is very important to have a better understanding in terms of the timing. And once you do that, I mean, based on your understanding of the design, are we talking about real timing violation, or these are expected timing violation, meaning that you have a clock domain crossing, for instance, but you covered that by design. So you may, at that point, add some timing exception to tell the software or the STA tool that don't look at this path. You don't need to analyze that path. I covered that by design. So that's kind of step 3, and very unlikely that you have hold time violation, but in some cases you may, and you need to do the same steps with the hold time analysis also, which is section 3 of the report. So I think following this process, you should be able to get a good process or a good methodology in terms of resolving any timing issue. And it is an iterative process. It's not a one shot and you get all your timing constraints resolved. It's iterative. So you go through the loop again and again. So you set timing constraint, you may change some timing, some tool setting to meet your timing, and then you check the timing report and you identify what the issue, and then correct the issue and or correct the timing constraints, and you go through it again and again till you get resolution, and that's how you get timing closure on your design. So it is iterative process, and we need to understand what's going on to be able to resolve any issue related to it. So in terms of reference document, so there's multiple reference document that are available, including training from the Lattice insights, where you can register for free. You can scan the QR code and connect you to the website. There's also timing constraint methodology user guide, so an application note that is available on Lattice website. The software guide for Lattice Diamond users. So the Indian software guide for Diamond users has some timing related information. Multi-kernel timing analysis, also technical note or application note 2063. Nexus family datasheet, there's timing information related to the specific Nexus family. The Radian help include all the syntax for all the timing exception and timing constraints. They will be listed in Radian, Diamond, the same thing. So there's a lot of information that is available to you in order to probably deepen your knowledge about timing, which stays a very important topic. I think need to have a lot of attention to avoid probably wasting time and hardware debugging. So and have more reliable design. So as a summary, I would say we've gone through the flip-flop, which is the most important element in synchronous logic. We looked at the meaning of metastability and how to avoid that situation, the STA process, and the two type of analysis that will be conducted by the STA tool, setup time and hold time analysis. We looked at the difference between timing constraint and timing exceptions. The timing constraint priority seen by the software tools and the different ways of resolving priorities associated with the timing constraints or timing exceptions. And we propose some timing constraint methodology to get to a timing closure. And obviously, don't forget about the Lattice Insights training library, where you can find a lot more information about all these topics and more to deepen your knowledge. So with that, I think we got to the Q&A question. I don't know how much time left we have. Let me take a look at the Q&A widgets. If you have any question, please put in the Q&A widget, and we'll try to answer. If we don't even get to all the answers today, we'll follow up with every single question that is listed there. So. Okay, so first question I see here. So what happened when you don't constrain all timing paths? So actually anything could happen, right? So all unconstrained paths in the design are not optimized and will not be reported by the STA tool. So the first thing, they are not optimized. So the tool has no target towards which it will optimize these paths, but they are not visible because the STA tool has no reporting associated with them. You'll see these paths that are not covered, but it will not have any score or any timing associated with them. If they have no timing constraint associated with them, then their priority to the tool is very, very low. So they will get placed at the end of satisfying all the other timing constraints, which make the implementation not predictable. They could have a long timing delays. They could have short timing delays. They could change between implementation. they could create issue in the hardware. So I think it's very important. It's really important to make sure that you have a high timing coverage of your design, and making sure that all your relevant timing paths are constrained by time constraints. So it's very critical, I think, to make sure that your design is fully covered. Is SDC file compatible between different vendor? Yes. So SDC is an industry standard format for entering timing constraints. So it stands for synopsis design constraint. If you if the vendor has not no specific timing constraint for them that is added into the SDC file, you should have portability between different vendors, different devices, and there should be no issue to use. Anyway, any timing constraint that we've seen today, the timing constraint and timing exception, they apply to all vendors. How do you constrain combinator logic, combinator paths? Let me say first, it is not recommended, or it's highly not recommended to have any combinatorial paths in your design, because the place and route of these paths will depend on each implementation. The delays may be different and so on. You could, though, have max delay, use it to constrain these paths. But if you change from device to device, if you change from technology, then these combinatorial paths will have different delays. So I think it's not reliable. Glitches will have an impact also on these combinatorial logic. So I would say you can constrain them, but they are not really recommended to use. It's better to have a synchronous design when it comes to FPGA. When do I need to use timing exceptions? I think we covered this in the previous section of the recommended steps for timing closure, the methodology of timing closure. I think if you have 100% coverage of your design and you meet your timing, no further need to add timing exceptions. You probably have over-constrained paths, even if they like we've seen in the 2 clock domain flip-flops, you have 400 megahertz timing constraint for your design. But if you meet that, yeah, I mean, doesn't matter. But in the case where you have a timing violation, or your SDA tool reports on timing violation, then it is very important to have these SDA, the timing exceptions, to reprioritize things for the software, so you can focus on the right area and optimize that and make sure you meet your timing. So they become more critical when you have a timing violation, and given it's a way to give the tool more indication about it, there's more understanding of your design. So the priority will be more on the most important things in your design. Is there training about timing closure techniques? Yes, I think there's a couple of courses, Lattice Insights, and there's, I believe, a session in the developer conference about timing closure by one of my colleagues, Sukruth. So if you can join that one, that would be great. So I cannot get over all the questions here, but make sure that we collect every single question and get back to you. I would like to thank you all for your time. Hopefully it was insightful and allow you to have a better understanding about the timing constraints. Please feel free to sign up to Lattice Insights and any other get any other information about this subject, and don't hesitate to participate in the other sessions that we have in the 3 days. So thanks for your time. Thanks for being part of the Lattice Developer Conference. Have a good day.